Hello everyone, welcome back to my channel. As you may have noticed, it's been a couple of months since I last uploaded some video content. I was basically busy with other activities the last few weeks, but hopefully we're back on track and you will see more videos in the coming days. For today, what I want to do is I want to share with you my own experience of the total solar eclipse that took place 2 months ago, a little over 2 months ago, in North America, the one on April 8th, 2024. And I would like to, discuss about this celestial event and also talk about why do solar eclipses happen, how often do we get them, why they're important, and other information that I can give you. Now, as you can see in this slide, this is not necessarily the eclipse that I witnessed. This is from another eclipse, but what you can see is the full disk of the sun that is being completely blocked with the moon. And you see these huge, beams or rays of light which form the corona of the sun, and these um, luminous parts of the sun that stretch to millions of kilometers outwards can only be observed during a total solar eclipse. We'll get to that later. So, from a historical perspective, when we go back to thousands of years, when people first, uh, saw solar eclipses or encountered solar eclipses, most of the time, and in many cultures, they didn't have any explanation for what was going on, especially with the sun. As we all know, sun is the main driving source of energy for all living beings on the planet. And thousands of years ago, just like today, all life depended on the sun. And uh, seeing that all of a sudden, in the middle of the day, the sun goes dark would have been a very frightening experience for people that were living centuries ago. And like many other natural phenomena, when you don't have an explanation, then you start making up stories, myths, legends, even the roots of many religions, and all religions, in my opinion, uh, is in the fear of the human mind in not being able to explain the natural world that they observe. So almost all cultures and all parts of the world, they came up with their own stories about what was going on with the heavens, and they even took it even further and started to, perform some religious ceremonies, do weird acts such as yelling at the sun, screaming, making weird noises, and even some cultures, mainly some tribes, they even started sacrificing animals and human beings just to remove what they thought was a spell on the sun, just to release the sun from whatever was, you know, taking it away from them. So I know that in East Asia there were legends of a huge, beast that swallowed the sun. Or in other parts of the world, we had similar stories. But if you go back to the cradle of civilization, which was in ancient Mesopotamia, uh, the Babylonians in particular, they did one important thing when it came to solar eclipses, as in any other, celestial event. And that was they started recording these events, registering these events on their calendars. And they came up with a period of, or cycle of solar eclipses that happened every 300 months or so. Although it wasn't completely accurate, but it gave them some sense of security, because when you're able to predict something, then your fear of that would be greatly, reduced, Uh, and uh, it was ancient Babylonians that started making careful observations of what was going on. If we fast forward to the modern era, we no longer are afraid of solar eclipses thanks to great minds such as these two famous gentlemen that you see there, the portrait of Sir Isaac Newton on the left and a picture of Albert Einstein. The reason I'm bringing these two figures is that although in order to understand what goes on during a solar eclipse, it doesn't really require to understand the general theory of relativity or even Newton's universal law of gravitation, but they had their own role, and I'll discuss about that shortly. So on the left, we see Sir Isaac Newton. He's probably the most intelligent and the most brightest human being that has ever walked on the surface of our planet. And in the 17th century, he came up with his laws of motion. He did many great, I mean, devised many great theories in physics. I would say he was one of the founding fathers of what we know now as classical physics. He did a lot of work in the field of optics, many different branches of physics. But one of his most well-known and celebrated, uh, you know, work and research was in understanding the force of gravity. Now, the irony here is that uh, Newton himself really didn't understand gravity. He just came up with a formula with an equation that explained gravity. And that equation, as you can see, it's right there in the bottom left corner of the slide here. F equals gm1 m2 over r squared. So he realized that the motion of heavenly bodies and also terrestrial bodies, like the tides and waves and the falling apples, or the, I would say, trajectory of projectiles, many different phenomena that he saw around him, he was able to make a connection between terrestrial phenomena and celestial phenomena through this law. And that's why we call it a universal law of gravitation. He realized that the force between two objects, the gravitational interaction, the gravitational force between two objects, only depends really on two things. One was the product of their masses, which you see here by m1 and m2, and the other one was by the inverse of the square of the separation distance between them. And for a long time, his theory of gravity was perfectly fine in explaining the motion of celestial objects. And even with the aid of his theory, we were able to discover, let's say, the planet Neptune. But in the 20th century, more than 200 years after Newton proposed his theory of gravity, Einstein came along and he came up with a radical new idea, a new theory of gravity, and he tried to explain what were the loopholes in Newton's theory. The first loophole was about what is this gravitational force really? I mean, in Newton's equations, you don't see any parameter of time in this equation, which means that if two objects are really, really far apart from each other, they still, attract each other by the force of gravity. And this attraction appears instantly. So it's like an action at a distance. And this was the major problem because we know that nothing can travel faster than the speed of light. And Newton himself, he actually realized that although he was able to explain gravity, but with the nature of this force, how this force operates, he wasn't capable of doing that. So he just swept it under the rug and kept it as a secret. But as I said, when Einstein came along, more than 200 years later, he came up with a new idea of gravity. In his theory, which we now know as the general theory of relativity, Einstein considered gravity to not be in the form of a force, but rather let's say, deformation of the fabric of space-time. Now, his idea is very complicated, and even for physics majors, it's one of those difficult theories in physics to really, learn and understand, both because the math is very complicated and the ideas themselves, they're quite, um, it doesn't make sense when you originally, deal with them. They're not so intuitive. But anyway, Einstein realized that gravity is not a, sort of external interaction between objects, but rather it's the result of the curvature of space-time. And he came up with his field equations. Here, I'll just, for those of you who are physicists, you probably know what this is, but for those who are not, this g mu nu is called Einstein's tensor. This lambda here is the cosmological constant. Lowercase g mu nu is the metric of space-time. G is the gravitational constant, which appears also in Newton's equation. C, of course, is the speed of light. And T mu nu is the stress energy tensor. So these two theories, right now, of course, we only need to use or to apply Newton's theory in order to, send space probes to the moon, to Mars, all other planets. We really don't need to apply the principles of relativity, the general theory of relativity, into, like, let's say, safely land a man on the moon. But why did Einstein even come up with this? One reason was, as I said, was the loophole inside the Newton's universal law of gravitation, and the other one was experimental evidence. Among all the planets, Mercury in our solar system is the closest to the sun. And because it's closest to the sun, it feels a huge gravitational field, that of the sun. And because of that, its orbit turned out to be slightly, only slightly, different from what Newton predicted. So the theory said something, and the observation said something else. And that's a problem in science. And when that happens, then you have to either improve the theory to explain the experiment, or you need to just throw away the theory and come up with a new theory. And what Einstein did, he actually, worked on this problem for years, and he came up with his general theory of relativity, which in fact uh, covers the Newton's universal law of gravitation in cases in which, let's say, the gravitational fields are not so large. So in other words, the general theory of relativity, in the limiting case in which you were not dealing with huge objects, would boil down to, or it would automatically tend to Newton's universal law of gravitation. So with his theory of relativity, Einstein's theory of relativity, he was able to, explain those little deviations in Mercury's orbit. All right. Um, now, again, if we fast forward to more recent times, as you can see here on the top left corner of the slide, I brought an actual picture of the most famous solar eclipse that happened in the history of science. It was a solar eclipse of 1919 in the island of Principe, or Principe, that depends how you want to pronounce it. Uh, this image is important because it allowed the scientific community to settle down the debate between Newton and Einstein's theories. And once we got the evidence, once we um, had solid and firm confirmation of the validity of general theory of relativity, then the scientific community accepted it. But it also has some other historical, importance, this figure. As you can see here, we have uh, two of the scientists. One is Albert Einstein on the left, the one on the right was, maybe you guys wouldn't know him. He's not as famous as Einstein, but his name is Sir Arthur Stanley Eddington. He was the brightest astronomer of Great Britain in the time during the World War I and the years after. And he, you know, led an expedition in the island of Principe with his team to take these photos. So this photo of the total solar eclipse in 1919 was taken by uh, Eddington. And by the way, this Principe is a little island on the west coast of Africa. And why this is important, but is because Germany and England, they were at war, right? And after the First World War, they had very tense political relations, and it was interesting that two scientists, they sort of uh, tried to bridge the political differences between the two nations. Now, the story is actually best, described in this movie, Einstein and Eddington, by BBC and in association with HBO. I highly recommend you to watch this movie. It beautifully, uh, shows all the events that led to that expedition uh, for chasing the solar eclipse. And apart from Einstein and Eddington, there are other, important figures in the history of science, such as Max Planck or Heaviside. These other, uh, scientists, they would also were interacting, and they all had their own role uh, in the events that led to the acceptance of the general theory of relativity. All right. Now, we don't need to know Newton's theory of gravity, and we don't need to know Einstein's general theory of relativity to understand how eclipses happen. All we need to know is first, according to Fermat's principle, in the vacuum of space, light travels in a straight line. That's the first principle that we need to know. And the other thing is a bit of geometry. And how do solar eclipses happen? I tried to show it in this simplified, a figure here. It's all about a perfect alignment of three celestial bodies: Earth, Moon, and the Sun. Now we know that the Moon revolves around the Earth, and you might ask, okay, if that is the case, then we should have a solar eclipse every month and a lunar eclipse every month, because once in a month the moon just moves around the earth and it can block the sun. But the answer to this question is that no, we don't have a solar eclipse and a lunar eclipse every month. And the reason for that is that the orbit of the moon around the earth is tilted with respect to the orbit of the earth around the sun. And therefore, both solar and lunar eclipses are incredibly rare events. Only once in a while these three bodies actually become collinear, or they lie on the same line. And when that happens, the shadow of the moon would fall on the earth. And as you can see here, we have this gray region, which is called the penumbra of the shadow of the moon, and that is regions in which the sun is not totally blocked. We still have daylight, but it's we can say that there's a partial solar eclipse going on in those regions. And then there's this little tiny region which the full shadow of the moon falls on the surface of the earth, and that is the umbra. And people that uh, chase eclipses are called umbrophiles. And umbra comes from the word, it has a connection to the word umbrella, right? So it's the shadow, it's the dark shadow of the moon, it's the umbra of the shadow of the moon that falls on the earth. It's a relatively tiny region in which, if you're in that region and the weather conditions are fine and there's no clouds in the sky, you can witness a total solar eclipse. Now, as I said, solar eclipses are rare, but they're even going to get even more rare as time goes on. And the reason for that is those of you who are familiar with the conservation of angular momentum, you would know that the moon is moving away from the Earth at a rate of a quarter of an inch per year, if I last recall. So that means that this umbra region would start to get tinier and tinier and tinier, and there will come a time in which the cone of the umbra would never touch the surface of the Earth, and we would never ever be able to see a solar eclipse. But that would happen millions of years, so there's nothing to worry about. But still, as I explained, solar eclipses are quite rare. Now, what makes it so special? What makes a solar eclipse so special? And this is a an interesting thing, and it's kind of weird that completely by coincidence, it turns out that the apparent size of the moon and the apparent size of the sun, as seen from someone on the Earth, they're identical. They both occupy half a degree in the sky. And why do I say this is strange and it's bizarre? It's because for two celestial objects to have the same apparent size as seen by a planet is a completely rare thing to happen. I would say it's just pure chance and coincidence. Maybe someone actually, I heard someone say that if aliens were ever to visit the Earth, one of their main, objectives would be to witness a solar eclipse, a total solar eclipse, because probably in their own planet, their moon is either too close to their planet or too far away from it, so it wouldn't actually fit their sun. It cannot completely block their sun. And if you look at these data, these numbers, you would start realizing why this is the case here. The sun's diameter is 1.39 million kilometers, so it's quite huge, whereas the moon's diameter is 3,500 kilometers. So as you can see, the moon's actual diameter is 400 times smaller than the sun's diameter. So if you look at the, let's say, equator of the sun, you can fit in 400 moons here, right? But at the same time, if you look at the distance of the sun from the Earth, it's 150 million kilometers, whereas the moon's distance from the Earth is just 380,000 kilometers. So again, the sun is 400 times further away from us than the moon is. So these two numbers, 400 times larger, but at the same time 400 times further away, make them appear to be exactly the same size in our sky. And thereby, when the moon passes between us and the sun, it can completely and perfectly eclipse the sun. And for the uh, solar eclipse of April 8th, 2024, this was the path of totality. By the way, we call it the North American total eclipse for the obvious reason that the path of totality, swiped three countries in North America: Mexico, the United States, and parts of Canada. And due to Earth's rotation and also the orbital velocity of the moon, this shadow uh, moves incredibly fast over land. Its ground speed is about 2,000 kilometers per hour. And the width of this shadow, or the region in which you have the total the solar eclipse or totality, is roughly 100 kilometers. If you do the math, you would realize that solar eclipses, perfect or total solar eclipses, will only last somewhere between 3 to 4 minutes. So it's an incredibly rare event in space, and also the duration of this event is very, very short-lived. It's limited. As I said, typically between 3 to 4 minutes. The most the longest total solar eclipse that was ever recorded was about more than 7 minutes, and so most of the solar eclipses that you see is around 3 to 4 minutes in duration. Now, the eclipse started on April 8th, 2024, in the Pacific Ocean, East Pacific. It made its way to Mexico and then entered the United States, passed through many major cities, so millions of people could have witnessed it, and then passed through parts of southern Ontario in Canada and other parts of the province of New Brunswick in Canada, and then it left towards the Atlantic Ocean, the North Atlantic Ocean. The only thing that mattered really for us, because the path of totality was close to where I live, it was the weather conditions on that day. So I had to keep, checking the weather condition and watching the forecast to go to a location in which the chances of having a cloudy sky were minimal. And the last minute, even yeah, right in the morning of the day of the total solar eclipse, most of Canada, where I live, they had cloudy skies. And one of the places that the forecast was good and was promising was a little town close to the US border in the province of Quebec, the town of Lacolle. Uh, it has a population of less than 10,000 people, so it was a very quiet and peaceful town. And as you can see, a couple of hours before the eclipse, I took this picture of where I set up my equipment. There was a little hill uh, in the middle of the town, and people started to, gather as we got closer and closer to the um, timing of the eclipse. But as you can see, we had some clouds, some scattered clouds and some large thin clouds, which they were causing some concern for me. But as it turned out, during the eclipse, the clouds were minimal. And as you can see, I set up two telescopes here. The smaller one, the white telescope, is a solar dedicated telescope with a built-in white filter, which allows you to safely observe the sun. And this other telescope that I set up was my main, optical telescope that I used, and that was an 8-inch telescope. And Here's a picture of me setting up my equipment. I also put a solar filter because it's very important, right? You never ever should look to the sun through a telescope unless you use proper filtering. If you don't use a filter, you would instantly burn up your retina, and it would be irreversible. So you will lose your eyesight. Even without a telescope, it's not wise to look at the sun. It's very bright. So I put my, I installed my solar filter, and this filter is a white filter. It blocks all wavelengths of the sun, and it actually filters out 99.9999% of the radiation that is coming from the sun. All right, so as the eclipse started, you see the moon was entering from the south west corner of the sun. I had the chance to take a few pictures with the telescope. This is a little close-up figure of the early phases of the eclipse. As you can see, we have some sunspots, and these sunspots they are related to cooler regions of the sun's surface. In another video, I'm planning to explain to you extensively what these sunspots are. And as time passed on, this moon, it started covering more and more of the sun. And here's another picture. And as you can see, the moon, now you can get a feeling that it has the same size as the sun. It can perfectly block it. So what you just saw or you heard was a little footage that I took. I recorded the video, and you saw that the sun and the moon were vibrating because there were strong winds. But nevertheless, we didn't lose the focus, and the sun, sorry, remained sharp. And I just wanted to, capture a live video of the event. And as you can see now, the moon is starting to, touch some of these sunspots. That was kind of interesting. I took pictures of that as well. And also, when the moon was almost completely blocking the sun, uh, I knew that there were other strange phenomena that were taking place. One of them is called the crescent shadows. They're images of the sun. They're images of the crescent sun. So if you look at the shadows formed by leaves on a tree, you would see that they look weird. They look like little tiny, crescents. Well, it was early in April, and in Lacolle, although it was springtime, but the trees weren't really covered with leaves, so I had to use a little tiny pinhole to cast the image of the sun on this, Coleman, and I actually managed to, form these little crescents, which were images of the sun. And you should know that this is only possible during partial solar eclipses. Okay, here's another image of the sun fading away and the moon that is actually moving to block the sun entirely. And finally, uh, at around 3:26 p.m. Eastern Time, the moment of totality happened. And this totality lasted for about 3 minutes and 20 seconds. It was my first time in my life that I was witnessing a total solar eclipse. And I was so excited, and I didn't want to waste time, removing the filter off the telescope. I just wanted to relax and enjoy the entire duration of the eclipse. So I didn't take any photos with my telescope during totality because, as I said, I didn't want to waste time, aligning the telescope again, putting the sun into focus, removing the filter. So this picture was actually taken by a iPhone 14 Pro camera, and it shows this glow around the sun, which is actually something that you can never see in ordinary conditions. This is the corona of the sun. The reason it's a little bit blurry is because there was still a little thin layer of cloud. But anyway, nevertheless, we were actually seeing, especially close to the sun's surface, you see these great rays which form the corona of the sun, and they stretched out for millions of kilometers off the surface of the sun. All right. Here are other figures. This one may not be so impressive. I tried to process the figures that I took with the iPhone Pro 14 camera, but these two are better figures. This one was actually an attempt to try to show you the prominences. During the total solar eclipse is the only time you can see these huge eruptions of plasma on the surface of the sun with your naked eye. Otherwise, you have to use a hydrogen alpha filter and a solar dedicated telescope to observe them. And it was quite interesting that I saw a rather large prominence in this corner of the sun uh, for a few minutes, and it was going on. If you look at other pictures, more professional pictures of the solar eclipse that happened on April 8th, 2024, you would actually see that, large prominence. And yeah, here's another picture of me right in the middle of the eclipse. As you can see in the distant horizon, we see this dim light. That is the penumbra of the moon. The rest of it you see is total darkness, and this is the eclipse sun. This is my telescope, and this picture was taken by my spouse. I really like this image because it shows me and my telescope under the eclipsed sun. It was a very incredible, the experience that I had. These other two pictures were taken from one of my friends that he was also present with me during the eclipse. He took his pictures from the phone, from his phone, and then later sent it to me. You can also again see this nice corona surrounding the sun. And one other effect that uh, happens only during a total solar eclipse is a 360-degree sunrise sunset effect. You see these, in ordinary sunrises or sunsets, the horizon looks like yellow, orangish, reddish, right? But it's only one horizon, where the sun is, trying to rise, or where the sun is setting down. But during the total solar eclipse, an entire 360 degree of this, sunrise sunset effect can be seen on the horizon. I'll show you a video. The video has I'm not going to talk on the video, but I'm just going to show this video, which was taken by my friend. And in the video, you also see me that I'm trying to look at the sun, and you see other people around that they too gather to witness this event. So I'll just play the video for you so you can, appreciate the whole 360-degree sunrise sunset effect during the total solar eclipse. All right, then right after the eclipse finished, most of the people that gathered in that little park, they just left, but I wanted to capture the entire event, so I stayed on and witnessed the final phases of the eclipse. And this is the very last contact between the shadow of the moon and the disk of the sun. And here's a close-up image of that last contact, and you also see a sunspot here. And yeah, that was it, the solar eclipse of April 8th, 2024. Now, there were other interesting things that went on during the eclipse. First of all, since the sky darkened, many animals, and bugs and insects, they became confused. They thought it was nighttime. So we saw a huge rise in the number of mosquitoes during actually, some of them really bothered me during the total solar eclipse. And the birds and everything, all these, little, animals, they went calm. They thought it was nighttime and they had to sleep. And yeah, as for the equipment that I used to capture this event, this is the telescope that I use. It's a Celestron Nexstar 8-inch solar telescope. Not a solar telescope, sorry. It's a it's an ordinary telescope, but you can use this filter, which I did, to block out most of the light from the sun. I also used a 32 millimeter eyepiece to, uh, attach my camera, the phone, to this eyepiece to take images of the sun. I also had to use a focal reducer, and the reason I needed that is because these telescopes, their focal length is not such that allows the sun to, you know, fit into the entire field of view of the telescope. So in order for that to be possible, I had to shrink the sun so that I would have it all in one, let's say, field of view on one frame, and that's why I had to use this focal reducer. And this, the Samsung Galaxy Ultra Note 20 was the one that I used in attaching it to the eyepiece and taking those pictures that you just saw. The next total solar eclipse is in mid-August, August 12th, 2026, and that is yeah, a little over 2 years from now. The reason I brought this light is that, you know, solar eclipses are they can be addictive. Someone said that to me before, but now it appears that I have been addicted to eclipses. And by the way, each different eclipse is unique on its own. So I'm really planning to travel to Spain to witness the upcoming solar eclipse. This eclipse, unfortunately, it wouldn't be witnessed for many. It wouldn't be observable for many people because most of the time of the eclipse is over the North Atlantic. It starts from parts of Greenland, goes through, southern Iceland, and then enters Spain, and then leaves off in the Mediterranean Sea. So it's really Iceland and Spain, and only parts of those countries that can actually see the eclipse. Uh, but the timing of the eclipse, which is in mid-August, and the location on over Spain, is a perfect location if you think about it climate-wise, because Spain has a usually dry, climate. There wouldn't be many clouds probably that day, and it would be a good chance for all eclipse chasers to gather again, and this time in Spain, and witness the solar eclipse. Now, I remember when I was much younger, about 20 years ago, more than 20 years ago, there was also another total solar eclipse. But at that time, my parents, they thought that I might hurt my eye by watching the eclipse. So all I was allowed to do was to sit inside the house and just observe the dimming of daylight. And since then, I always wanted to, observe a total solar eclipse for myself. And finally, uh, after more than 20 years, I had the chance. I was lucky enough to be in the right place in the right time with good weather conditions to, observe this awesome celestial event with my own eyes. And, these pictures, the footage I showed you, all these words that I tried to say about the solar eclipse, they really don't do justice. It's something that you have to experience for your own, right? I can only give you a little bit of interest, raise your interest in observing this event. The actual thing is much more, interesting than what I had to say in this video. Anyway, nowadays, unlike ancient times, we are no longer afraid of celestial events such as solar eclipses. We're in the 21st century where science has provided us with the proper explanation of what's going on. It's not like the gods are angry at us. We don't need to perform any rituals or do any sacrifices. We're not scared of solar eclipses. But during the solar eclipse that I saw, for one moment, for a short amount of time, I tried to put myself in the ancient people's shoes, and I realized that, yeah, it indeed was a frightening experience. I just looked at, and it's an image that I would never forget. All of a sudden, you see the sun that is turning black, and yeah, that could be very scary for people that don't understand why solar eclipses happen and how they happen. So yeah, it was no wonder that ancient people, they were frightened of these events, and they started to behave weirdly, do very, sometimes brutal actions, and they started killing, animals and sacrificing them, even fellow human beings. So we're lucky that we're living in a time in which I would say most people are no longer afraid of solar eclipses. They can gather in hundreds on beaches and public parks to, celebrate and watch these interesting celestial events. And like always, please leave your comments in the comment section. Please subscribe to my channel if you find the video content to be interesting. I would love to hear your thoughts about, you know, eclipses, or if there's something that you want me to, make a video on or describe, just let me know, and I would be more than happy to do that. Remember, we live in a time in which we have to protect our scientific advantages and progresses, and we don't want to go back to the dark era. Now, every now and then we hear that some parts of the world, or I mean, in the world, in every corner of the world there are like you know, things going on that they're kind of scary, and especially on the media, you hear on the news, or sometimes when you surf the web, you see a lot of misinformation and disinformation circulating around. And I think it's a job of, I mean, scientists or people that have an academic background. They have a responsibility to try to advocate science, try to spread science in order to, uh, prevent, superstition and disinformation to circulate around. Because if we go back to the Dark Ages, then maybe a fun event such as a solar eclipse would turn out to be something very, you know, frightening. And it's not just about these natural phenomena. Uh, from a political point of view, we also don't want fundamentalism to grow and to spread around the world. We know that if there is one activity that can bring us together is through science. And look at this. All people, they look at the sun at the same time during an eclipse, no matter what their religion is, what their race is. They, for a few short minutes, they get the chance to celebrate something together. And we during those times is that we realize that we're part of a much larger and greater universe than our old selves. One more word before I finish this video, and I forgot to mention, when the sky became dark during the total solar eclipse, I was able to see two of the most brightest planets of our solar system, Jupiter and Venus. And Venus was much more impressive. And the reason for that is that usually when you want to, observe Venus, since it's close to the sun, you can only do it right before dawn or right after sunset. In other words, it never goes high up in the sky. It's always close to the sun. But during the total solar eclipse, the sun is completely blocked by the moon in the middle of the day, so it's high up in the sky, and then you can see Venus right above your head. And that is interesting because you never get to see Venus at that place. And it was interesting. For one moment, I realized, yeah, it's not. I mean, daytime is sort of something like an illusion. The reality is that space is dark. It's only because of the Rayleigh scattering of sunlight that we see the blue sky. Otherwise, it reminds you that we are in this great cosmic dark. So if you enjoyed this video, please don't forget to subscribe. And until the next content, take care of yourself and bye bye.